Hello, everyone. Welcome to a new year, new academic year of IOA Colloquia. So also, I hope everyone can see okay. We've gone dark because we're going to have some pretty galaxy pictures in this talk. So I'm delighted to welcome Dr. Enrichetta Iodice. I'm going to hand over to Elizabeth to give more of an introduction as she is a collaborator of Enrica's. So without further ado.
Thank you. Hi, everyone. Thank you for being here. Today, we have the great pleasure of having Enrica Iodice with us. So Enrica is a professor at the University of Trieste in Italy at the Astronomical Observatory of at the Astronomical Observatory of Capodimonte in Napoli, and also at the University of Vanvitelli in Caserta. Enrica is also the head of the INAF Coordination Center for the VLT Survey Telescope, the VST. And she did her master's in Naples as well, in Federico too, as well as a PhD both in Italy, in Trieste, at the International School for Advanced Studies, and as well as the University of Wisconsin-Madison in the US, before coming back to Naples for a postdoc and for a professorship. Yeah. So the floor is yours. Thank you very much.
Thank you very much, Elizabeth and Matt. The pleasure is mine. And during my talk here, I would like to present this project. The name is Levis. I know that the pronouns is not English, but I prefer to take the Italian pronouns for this project. And it stays for looking into the faintest with MUSE. This is a project focused on ultra-diffuse galaxies, which are really low surface brightness galaxies in the universe. And Levis is made by a big team of scientists with many experiences and many young scientists, including PhD students and postdocs. Levis is an ISO large program approved in 2021. We got more than 133 hours of time at the MUSE, the Intergral-field spectrograph working at the ISO VLT, to study a complete sample of ultra-diffuse galaxies in the Hydra I cluster. The power of this project is that Levis is the first homogeneous integral-field spectroscopic survey of UDGs. This is the outline of my talk. So first of all, the context. Why we study ultra-diffuse galaxies? And I will mention the state of the art, not only for observations, but also for theoretical predictions. And then I will briefly introduce you the target of this study, which is the Hydra I cluster. And finally, I will show you the groundbreaking results that we are finding with Levis. I think that you know better than me about the lambda cold dark matter scenario of galaxies and structure formation in the universe. And we know that the remnants of the mass assembly is found in the low surface brightness features in terms of tidal tails and stellar halos around the brightest galaxies, but also many small galaxies that are satellites around giant galaxies. You also know that this model postulates a number of many low mass dark matter halos, and prediction says there are predictions on a number of galaxies that should be associated to low mass dark matter halos. And we know that observations say something different. Different in which terms? That we are observing a smaller number of low mass galaxies with respect to the predictions. And so the question is, we are, the gap is because we do not have a powerful telescope to move at the very low surface brightness galaxies, the theory is wrong, or both. So that's the reason why astronomers are interested in the low surface brightness regime. What about ultra-diffuse galaxies? Ultra-diffuse galaxies, this is one of the most famous Dragonfly 44 discovered by Colloquium and collaborators 10 years ago in the Coma cluster, and they are the lowest and largest galaxies known in the universe. The peculiarity, they are defined, empirically defined to be faint, where the central surface brightness should be lower than 24 magnitude per second square in the G band, and an effective radius larger than 1.5 kiloparsecs. They have a stellar mass that is comparable with the dwarf galaxies, but the effective radius are comparable with the effective radius observed for giant, bright, late-night galaxies. You can understand that having a sharp cut in the structural parameters is not really a physical approach, because if you measure a central surface brightness of 23.8 plus an error for a central surface brightness of a low surface brightness galaxies, you can say that this is not a UDGs, you have an error. So you need a more physical approach to select the ultra-diffuse galaxies. And this approach was introduced studying the low surface brightness galaxies in the Virgo cluster, and they realized that the low surface brightness galaxies, including the UDGs, are the extreme ends of the distributions in the structural parameters of the dwarf galaxies populations. So they populated the 2 sigma age. So what about the parameters, the structural properties observed for ultra-diffuse galaxies until now? We know that about color, integrated colors, we observed that ultra-diffuse galaxies red and quenched, mainly located in the cluster, but bluer ultra-diffuse galaxies are also observed in low-density regions. The kinematics is one of the field for which we have a very low few measurements. To date, most of the UDGs seems to show a low velocity dispersion. This is something expected from the Tully-Fisher relation, since they are low surface brightness system. And to date, there are no many measurements regarding the stellar motions, and so the stellar kinematics. The stellar population suggests that they are old and metal poor. However, few objects are found to have ongoing star formation, so there are also younger ultra-diffuse galaxies. The globular cluster content is one of the most attractive field of research, because it seems that some UDGs, in particular those studies in the Coma cluster, show a specific frequency, I mean the number of the globular clusters per luminosity, higher with respect to the value based on the total luminosity. The majority of ultra-diffuse galaxies have anyway a dwarf-like specific frequency. The dark matter content for these objects is the most debated topic, because Van Dockum, when introduced the first study on UDGs, suggested that this faint and diffuse object should host a huge amount of dark matter, since they have to survive to the tides in the cluster core. So we were able to constrain the dark matter content in UDGs, mainly to date from the globular clusters content. And it seems that we have UDGs that are dark matter dominated, UDGs that show a dwarf-like dark matter content, but there are also UDGs that seems to do not have any dark matter. So you could imagine that all these, the wide range of observed parameters cannot fit in a unique formation scenario. So there are several formation channels to produce a ultra-diffuse galaxies. What they are? We have the first proposed scenario was just from Piet van Dokkum, suggesting that an ultra-diffuse galaxies might form from a high surface brightness galaxies that lost the gas supply at an early epoch, and so no more fuel was available for the star formation, so the galaxies was just cooled and quenched. This formation scenario was named the failed galaxy formation for UDGs. In this scenario, we expect that UDG is red, is quenched, metal poor, and is also dark matter dominated because the dark matter of the high surface brightness galaxies is still in place. At the same time, recently, different formation scenario was also proposed where a ultra-diffuse galaxy can form just from a puffed up process of a pre-existing dwarf galaxies. How a dwarf galaxies can expand? There are two processes. Internal processes that the proposed one was the strong supernova feedback that just push the gas outside, and also a high spin dark matter halo that just induce the expansion of the galaxy. In this case, we expect that the UDG should still have some gas, but mainly located at larger radius, and has a dwarf-like dark matter halo because the progenitor is a dwarf galaxy. In the external processes that are mainly due to the gravitational interactions with the environment or with the galaxies in the cluster where they reside, in this case, the dwarf galaxy, the gas in the dwarf galaxies is removed, and the dark matter content and the metallicity are a function of the environment because this depends on the location of the galaxies of the progenitor. This is not the whole story because ultra-diffuse galaxies could also form in the same processes where tidal dwarf galaxies forms. I mean, in the clumps, stellar and gas clumps of tidal tails of merging galaxies. Tidal dwarf galaxies have been observed, and in this work of Piralen in 2014, if you look at his table 1, there are galaxies that have the structural parameters consistent with an ultra-diffuse galaxies. He didn't name these galaxies as UDGs that were introduced later by Van Dokkum. But anyway, they were already known at that time. Recently, studying the jellyfish galaxies, the group led by Poggianti and collaborators, they suggested that ultra-diffuse galaxies might also form from the gas clump, only gas, that is stripped during the room pressure phenomena. Till now, there are such kind of galaxies are not observed yet. For both of these formation channels, we expect that UDGs do not have any dark matter, and they are bluer, they might have dust, have a moderate metallicity because they form from a pre-processed material, and they might have UV emissions related to the stellar formation, to the star formation, and might also have a gas. So, recently, Luisa Buzzo published a work where she tried to put together all the observations for ultra-diffuse galaxies. Observations, I mean metallicity, photometry, globular cluster content, and she suggested that the puffed up dwarfs have different observed properties from the failed galaxies. In particular, the puffed up dwarfs are metal rich and follow the mass metallicity relations and are also older than the failed, the UDGs that reconciled with the failed scenario. So some progresses are done. So which are the observables to discriminate between the several formation scenarios? First of all, we for sure need to detect the UDGs, so we have to study the light distributions and colors, and also detect candidates for globular clusters. But the kinematics really makes the difference, because from the spectroscopy, we can get the stellar kinematic, the star formation history, and the dark matter content, including the globular clusters confirmations. The first data, integral field data to study an ultra-diffuse galaxies, was published by Eric Emsler in 2019. They acquired MUSE data for Dragonfly 2, which is a nearby ultra-diffuse galaxies, and this was the first two-dimensional map for the line of sight velocity, where they didn't find any remarkable gradients for the velocity, for the star rotation. So the idea was that ultra-diffuse galaxies do not rotate. And you can imagine, if you consider that these systems are all pressure supported, deriving the dark matter content from the velocity dispersion, you have a biased value if in the opposite case, there are some rotations. So the Lewis project is was just thought in this direction to obtain the integral field spectroscopy for a sample of UDGs, not just one target. And the first goal was to confirm the cluster membership of detected ultra-diffuse galaxies in the Hydra I cluster, and our goals were to derive the stellar kinematics in order to constrain the dynamical mass and the dark matter content, to address the stellar population, to study the star formation history, so the age and metallicity, and also to confirm the globular cluster content and have an independent measurements, estimates for the dark matter. What about Hydra? The Hydra cluster is a rich cluster, very massive. It is located at 40 megaparsec from us in the south hemisphere. This is the core, and these are some other bright galaxies. Hydra is made of three main subgroups. The core, which is the most, where there is the highest density, this is also the X-ray emissions, plus a north overdensity, and the southwest group, which is a falling group into the cluster potential, so it is foreground. These are in one shot the main structure of the cluster, because the core is dominated by the huge diffuse light around the brightest cluster member in the core. In the north, we detected, this has a filamentary structure. These are all bright galaxies in the cluster. And we detected here many peculiar morphologies in the galaxies. On the other hand, the faintEst group is, we detect a lot of ongoing ground pressure stripping. So many phenomena, and improving the detection of low surface brightness galaxies. In the cluster, we detected new 200 low surface brightness galaxies. Most of are dwarf, but 24 are UDGs like this one. This is the Lewis sample. They are all the red boxes. And just to give you an idea, we have 30 targets. So we have both very low surface brightness galaxies and UDGs. And the range of a limiting magnitude is 24 down to 27. And to reach a signal to noise larger than 10, we had to exposure, we have an integration time that ranges from 3 to 6 hours on target. Have a look at the sample. This is let's say a typical ultra-diffuse galaxies. This is the region where you have the central surface brightness lower than 24 and effective radius larger than 1.5. But interestingly, we can map all the other regions around. So we have galaxies that are really extended dwarfs, and the most interesting objects are those that are located in the transition regions between UDGs and the dwarfs, because we are really interested to see if UDGs might form from dwarf galaxies. So the value of Lewis is just that we can map the whole environment, so the cluster from the core to outskirts, and also several kinds of morphologies. First of all, we have confirmed that whole UDGs and LSB are really cluster member, because we assessed the cluster membership just based on the color magnitude relations. But with the Intergral-field spectroscopy, we have confirmed that they are all cluster members, and we derived the phase space. And we noticed that the galaxies with a distorted irregular morphology are mainly located in the late infill region of the phase space. This is one of the UDGs of the sample. I have chosen the best spectra to show you, and this is the stacked spectrum inside one effective radius. And you can notice that we are able to measure only 3 main absorption lines that are the H beta, H alpha. This is not the case, but in some cases we see magnesium, but it's very, very weak. And when we are lucky with the sky subtraction, the calcium triplet. This is in line with the fact that these galaxies are metal poor. And so have a look at the results. The first question is, do UDG rotates? Because now we have the two-dimensional kinematics map. So we have derived using the Voronoi beam, and beams are made with a signal to noise larger than 10. We have, in some cases, like UDG 11, we didn't find any gradients for rotation velocity. But we found other cases where a mild gradient is detected. On average, looking at all UDGs in Hydra, there is half of the sample that show rotations. And this is the first time that such a large fraction of UDGs showing rotation is detected. And this poses serious doubts on the dark matter estimates, because Until now, the dark matter estimate is based on only on the velocity dispersion. But if you want to account for the line of sight velocity distribution, you have to take into account the velocity dispersion and the rotation velocity. So the dark matter estimate is biased. Anyway, this is a comparison of the velocity with respect to velocity dispersion for UDGs compared to dwarf galaxies for which also exist integral-field spectroscopy. This sample is from the SAMI survey. Looking at the Tully-Fisher relation, you see that most of the ultra-diffuse galaxies follow the Tully-Fisher relation, the Fabre-Jackson relation for dwarf galaxies. But there are some objects for which we have a comparable values in the velocity, in the rotation velocity and velocity dispersion, and the UDGs, which are rotation supported, clearly fall in this region of the diagram. Looking at the dark matter estimate, in this plot we have compared the dark matter estimate with the dwarf galaxies in the local group, and we have selected this sample because they derived the dark matter estimate using exactly the same approach that we did, so just to be consistent. And we derived that on average ultra-diffuse galaxies and LSB in Hydra are dark matter dominated with respect to the dwarf galaxies in the, of a similar luminosity. Move to the stellar population stuff. This is the subject of a PhD student in my group, and he derived the stellar population for all UDGs and LSB in the sample. This is the age metallicity, where you can see that we have, looking at the phase space, we have on average that in the early infall galaxies on average have a higher metallicity than galaxies that are located in the late infall region. And this is something expected if you think at the typical relation that it's also valid for bright galaxies. Look at the mass metallicity relation for dwarf galaxies and also for high redshift galaxies, and I will explain this in a while. The Lewis sample on average agreed with the mass metallicity relation for dwarf galaxies published by Kirby et al. In 2013 with some differences. There are few galaxies that show on average higher metallicity than the others, and with respect to the mass metallicity relation. According to some recent works, the ultra-diffuse galaxies in literature that are that agreed with the high redshift mass metallicity relation seems to reconcile with the scenario of failed galaxies. And in this region of the Hydra cluster, we do not see any very low metallicity for ultra-diffuse galaxies. We have also derived the star formation history from the fit of stellar population. And we noticed something interesting between the galaxies that are in the early infall region of the phase space with respect to the late infall. And if you look here, the time where the galaxies have reached the 50% of mass and 90% of mass in the early infall regions is 7 and 11 gigayears respectively. And something similar happens for the galaxies in the late info region. So they almost form at the same time. But I'm sure that you already catch some differences. And the difference is this one. The time to produce the 90% of the mass from the 50% of the mass. This time is longer for galaxies that are in the early info region with respect to galaxies in the late info region. So the formation process was probably different for the galaxies in the two different regions of the cluster. Yes. So looking at the stellar kinematics and at the stellar population, we have realized that we have two classes of UDGs. What I mean? The stellar kinematics suggests that there are rotation-supported UDGs and dispersion-supported UDGs. From the stellar population, we have metal poor, metal rich, that are different between the two regions of the cluster. So let's see if there is any correlations. So are the two different kinematics and stellar population classes related each others? So the UDGs with rotation are distributed everywhere in the phase space. So there is any correlation with the environment. On the other hand, most of the pressure-supported UDGs are located in the early info and have higher metallicity. What about the dark matter? The dark matter dominated UDGs are all located in the early info regions, while the dwarf-like dark matter content are equally found in the early and in the late regions of the phase space. What about the star formation histories versus kinematic? This is another interesting differences, because we see that the galaxies that do not rotate formed star very quickly with respect to galaxies that show some rotations. So indeed, we are looking at two different classes of galaxies if we put together stellar population and stellar kinematics. So in the late info region, it seems we have a single population of objects, because we have galaxies that show rotations, have dwarf-like dark matter halo, and we have a fast formations of stars. And all of them have a metallicity consistent with the mass-metallicity relation. A mixed situation is happening in the early info, in the core of the cluster, because here we have both galaxies that show rotation and are pressure supported. We have dark matter dominated and dwarf-like dark matter galaxies. We have here a prolonged star formations, and we have galaxies that agree with the mass metallicity relation, and we have a few objects that show higher metallicity. So in this region, we can say that we have two groups of galaxies depending on these processes. On the other hand, in the late info, we have a single population of channels, single population of galaxies that probably all these properties reconciled with the puffed up dwarf. That is the same for one of the group we observed in the early info regions. And one thing, the galaxies that show higher metallicity probably formed through a tidal interactions with a galaxies or with the environment. What happens for the globular cluster? The globular cluster content in UDGs is the subject of another PhD work from this student, Marco Mirabile. The paper was just published. It is in the archive. And the ultra-diffuse galaxies in Hydra show, I think that a bunch of them show numbers of globular clusters between 2 and 11 for each galaxy. So the first step was to establish the membership of a globular cluster in UDGs through the redshift, and then estimate the specific frequency and so constrain the dynamical mass. Marco put together the MUSE data plus the deep images to have the best selections based on the colors for the globular clusters. And results, he focused on the brightest and high signal to noise MUSE spectra. And this is the results for these 4 UDGs in the cluster. And we found that 3 UDGs has a specific frequency that is consistent with the other globular cluster rich UDGs in other cluster, except for only one sample. And so the dynamical mass estimate based on the globular cluster study confirms that they are dark matter dominated. So the values are consistent with those we derived from the stellar kinematics. Finally, to conclude this talk, I wanted to show you 2 special cases that we have inside our sample. The first one is UDG6, where the spectrum, this is the deep images for UDG6, and this is the MUSE white image. And the spectrum stacked inside one effective radius show emission lines. So we observed H beta, O3, strong H alpha, and S second. And so we supposed that there is ongoing star formations in these UDGs. This is the only one of the sample. And this is the distribution of H alpha and H beta on top of the body of the emissions. And this is the distribution of O3 and S second. From the H alpha, measuring the flux in all these regions, they are consistent, looking at the BPT diagram, they are consistent with the star-forming galaxy. So indeed, there is a star formation ongoing in this object. We have derived the 2-dimensional map for the velocity of the gas in this galaxy, and there is rotation in the gas. This is the rotation velocity along the major axis and along the minor axis. This is the topic of a master thesis of a student, and we hope to publish these results quite soon. Finally, this is another really interesting object, the UDG32, which is located in the southwest group of the cluster. This is the region we are focused, and this is the system of galaxies, NGC 3340A and B. This is a system of two galaxies. They are on top of each other along the line of sight, but they are distant 2,000 kilometers in redshift. We have discovered using deep images that this is also jellyfish galaxies with an extended set of stellar filaments, more than 50 kiloparsec. And if you look really in the south, you see this yellowish cloud, and this is a UDGs. This is very extended. The effective radius is 4 kiloparsec. It's very faint. The central surface brightness is 26 magnitude per second square. And this object triggered our attention because the question was, is this a UDGs formed in the gas clump of these ultra-diffuse galaxies? If yes, this should be the first observed. And so we tried to analyze the MUSE data for this object. This work was published by Johanna Ark, another member of the LEVIS project. This is the how we can confirm that the UDG is formed from the gas clump? First of all, the redshift should be the same of the filaments, and we should exclude that the galaxy is just background or foreground. Second, it should be should have a younger age and matter rich than the other UDGs of the cluster because it is formed from a pre-processed material. And finally, it should not have dark matter. All things that we can probe using the MUSE data. This is the MUSE white image, and when we look at this, unfortunately, there is an extended emission H-alpha just on top of the ultra-diffuse galaxies that prevent most of the analysis. So we had to focus on a tiny regions here to get at least the redshift of the galaxies. And we measure the H-alpha only. So the results was the following. This is the redshift of the parent galaxies. This is the redshift detected by using H1 from the filaments. This is the redshift that we detected for the H-alpha filaments. And this is the redshift for UDG32. So they are cospatial. And this is the redshift for the two globular clusters that seems to be part of the galaxies, but they aren't. So they are intra-cluster globular cluster in Hydra. So at least the UDG32 is there. So it is cospatial with the filaments. What about the metallicity? Unfortunately, we cannot measure the metallicity and age from the spectrum. So we used the spectral energy distribution using also optical data. And compared to the other UDGs in Hydra, UDG32 indeed was younger and matter rich than the other values. We cannot say anything about dark matter because from this spectra we cannot derive at least the velocity dispersion. So this is still an open question, but it would be the fundamental parameter to finally confirm that these UDGs formed from the gas clump in the jellyfish galaxy. So my conclusions, with the LEVIS project, we have found for the first time that UDGs can rotate, and we have a bimodality inside the cluster. Most of the UDGs are dark matter dominated, and age and metallicity are on average consistent with the dwarf galaxies. And there is a gradient anyway in the star formation history. We observed two kinds of star formation histories for UDGs. And the structural properties are function of the environment. So we have a single population of the UDGs in the late infall regions, while at least there are two different formation patterns for UDGs in the cluster. Plus, we have two kinds, two special cases, one star-forming UDGs and probably one UDG is formed from run pressure stripping. So if you would like to stay updated with the LEVIS results, you can check the website where we are updating results. But I wanted to finish this talk saying something about the future. You have understand that we need many, many observables to study the different formation scenarios for UDGs. Right now, we have more than 3,000 UDGs discovered using deep images. So we have good statistics for structural properties based on images. Unfortunately, we lack spectroscopy. The available spectroscopic data, including LEVIS, is something 100. So 1 order of magnitude lower with respect to the photometry. We completely miss measurements for gas content, in particularly the H1, the UV emission that would map the star formations, and also the structure of UDGs with redshift. All the data we have are mainly in the local universe. So there are all these parameters can be measured with the upcoming facilities, in particular with the ELT, and I'm sure that Euclid and JWST can provide structure of UDGs with redshift. I'm done. Thank you.